Right, in this video, we're going to talk about flip-flops, pretty important stuff. We're going to use the latches we learned in the previous video to build up flip-flops to be used for sequential logic. So the first one, before we dive into the circuit for flip-flops, we need to know what is a logic, what is a clock. So clock is like a pulses or logic signal being used in the digital system for triggering the digital operations to happen in the circuit. So there's very typical clock looks like this. They're just voltage pulses, right? But being used for different purpose. And now here, this is called low, this is called high, and that's called a rising edge. This is called falling edge. And here, if this is T1 and this is T, for example, since you know this is in time domain, right? This is being plotted in time domain. And if this is T, this is T1, then what's going to happen is T1 over T will be the duty cycle. You may have heard this somewhere else. This is called duty cycle. And here, the duty cycle is 50%. And 1 over T is called the frequency of the clock. And there's another thing you need to know. If we have a clock like that, and sometimes you have a rising edge and falling edge, and in flip-flops, there are 3 types of triggering properties or triggering methods. Triggering methods. So here's a level, right? So here's a rising edge, falling edge. So they are edge triggered or level triggered. And in edge trigger, you have rising edge triggered or falling edge triggered, right? So which means the edge is going to trigger the operation for the movement of the logic. And level can be level 1, level 0, you know, and edge triggered can be rising edge, falling edge. So that's just basic fundamental concept you need to know before we move forward. And now let's take a look at the SR flip-flop, which is the first one I want to introduce to you guys. SR flip-flop. And you tell me what's the difference between a flip-flop and a latch we learned in the previous video. Okay. This is called clock, CLK. So that's an SR flip-flop. And you also have a Q as an output, Q bar as an inverse version of the output, right? So what's the difference between the SR flip-flop and SR latch? What's the difference? So SR latch is actually static. You couldn't control the sequence of the inputs to be delivered to the circuit. If you turn it on, everything will run automatically inside the circuit. However, in SR flip-flop, this is a clock-controlled device. It's a clock-controlled device, and you can use a clock to control the sequence to be delivered to the circuit after that. So that's the difference between the SR flip-flop and SR latch. And you can see that this part is actually SR latch, and you add these two NAND gates and put a clock here, and you are going to have a S and R here. And why is S and why is R? It's kind of like flipped compared to the SR latch. You used to have R here, S here, right? But now it's different. So the reason is you have a NAND gate which is trying to invert your signal, your control set and resetting signal here. So when you are having an S, after it's being inverted, you are actually getting a R here. So this is still R, this is still S. But here at the final input, this S is R instead, because you have an inverter here. Okay. And so when clock is 1, so this is a level triggered. So this guy is a level triggered SR flip-flop. Okay, so level triggered. So when clock is 1, so which means you have a level 1 is going to trigger something, right? So what's going to be triggered? S and R will be inverted and delivered to the latch inputs, right? When clock is 1, so 1 is not affecting the result of the AND gate or NAND gate. So S and R will pass this to NAND gate and being inverted and being delivered to the input of the latch. Okay, so S becomes R, R becomes S. That's it. When clock is 0, what's going to happen? So 0 will kill the two NAND gates. You have two ones here. We'll have two ones for the latch. It's not affecting the NAND gates for the latch. So you are having a memory. It's at the memory status. It behaves like a memory. Okay, so that's the behavior. That's it. You just have a clock to control this set and reset signal to be delivered to the latch. So there's nothing different other than that compared to the SR latch we learned in the last video. Okay, you just have a clock to control it. Okay, and so what's if we put everything in the truth table? What's that will look like? What that will look like? Truth table. Clock S R Q bar. Let's summarize the logic in one table. Okay, if you have clock is 0, doesn't matter whatever are these things. It's going to be a memory. So you're going to get a Q here, Q bar, whatever their previous status are. It's just the memory. And then the next day, when clock becomes 1, let's start with it. 0, you can have 0, 0, 0, 1, 1, 0, 1, 1. You have 4 states you want to analyze. So when clock is 1, these two will be passed through the two NAND gates in the front, and then you have 1, 1 for the latch. So when you have 1, 1 for the latch, it's a NAND gate latch. So it's going to be a memory as well. Okay. And for this one, SR, so which means you are resetting the circuit, right? So you are going to have the output to be reset. If you have set, you are going to set the circuit. And if you have 1, 1, then they are going to be inverted after the front two NAND gates, and you are going to get 0, 0, right? So 1, 1 here, 1, 1, and clock is 1. So 1 will be inverted. You got 0, 0, 0, 0 will kill the NAND gates here, and you are going to get a 0, 0 for the two outputs, which will be invalid. The reason is nobody will use it. Electrically, it's making sense. It's going to work. However, nobody want to use it. It's totally invalid. Okay, not used. So that's a truth table for that SR latch. Next, there's another topology of flip-flop of one of the flip-flops, which is super useful. You can see this everywhere because this topology just performs like a data transfer or short-term register or memory. You can control if you want the data to be transferred through that block. So you can control, it's like a switch or just data transfer. Okay, it's called D flip-flop. It's a data flip. So D means data, right? So which means it's just trying to transfer the data. Whatever in the data pin, it's going to be transferred to the output. And for example, so the block looks like this. So the way to make a D flip-flop is use the SR flip-flop and connect the inverter between these two pins, and you have a Q here, Q bar here. That's it. Okay. Of course, you have a clock. It's level triggered, right? And we're going to learn a different type of D flip-flop. But right now, we are using the previous SR latch to control that. So that's a D pin. Whatever here will be, it's going to be transferred to Q. Let's see if this is right. So for example, if we have, so if D is 1, so at clock is 1, what's going to happen? So 1 here, 0 here, you're trying to set the result, right? So Q will be set, Q bar will be 0. So which means D is 1, result is 1. So it's like a data being transferred to the output, right? So that's the data. Another case, if D is 0 at clock equals to 1, when it's getting triggered, it's a level triggered flip-flop, what's going to happen? So if D is 0, R will be 1. So we are resetting the circuit. So Q will be 0. Q bar will be 1. If D is 0, if you just look at input and output, you have an input as 0 and output is 0. It's exactly transferring the data at the pin of D to the result. So that's why we call it's a D flip-flop, because it's transferring the data to the result. Okay, and the circuit, if we don't draw this logic box over here, if we draw the real circuit of it, that will look like this. Clock, and you each invert these two pins. Here's clock, here's Q, here's Q bar. That's it. So that's a version 1, right? That's a D flip-flop. However, it's a version 1. It's a level triggered. So it's good to know this. And that's the second. So we have SR flip-flop, D flip-flop. And you can see what's the benefit by using a D flip-flop. Another benefit here, which is you can get rid of the invalid status. Since you always have your S and R being inverted, you never get a 1, 1 over there. So see, remember that your SR flip-flop, when you have a 1, 1, it's invalid. You don't want that to happen. If you have this, that will never happen. So this can get rid of the invalid status. All right. Next flip-flop topology I want to introduce is the JK flip-flop. So it's developed by Jack Kilby from Texas Instruments. So this topology was developed in this year, okay, being invented. So he added a little feedback to the SR flip-flop we just introduced, and it looks like this. So this can also get rid of the invalid status, and I will show you why. This can be a little confusing, just be careful, right? Just pay attention at how I do the analysis. And what he added to it is a feedback. So from here to the input, and from here to the input here, right? And the name for this tool won't be S R again, it's going to be J and K, because this is a JK flip-flop right now. And now let's see why. Pay attention, this can be confusing. If you miss that, you know, it's you won't be able to know why. Yeah, it's so confusing. I have so many feedback. So the output is going to affect the result of, you know, the will be affected by the result of the previous output. It's kind of confusing. So now let's see how this can work properly. Okay. So when clock is 0, what's going to happen? Let's start from something simple. So if clock is 0, what's going to happen? Let's see. 0, so 0 will kill the Nand gate, and you are going to have a 1, 1 here, right? 1, 1 won't affect the Nand gate, which means whatever here is going to be here, it will be like that as well. So Q, so 1 will not affect the Nand gate here as well. So Q will be inverted, get the Q bar will be inverted, get the Q, which means it's a memory. Not too bad so far, right? So if clock is 1, what's going to happen? Let's see. When clock is 1, so the 2 NAND gates are being enabled, right? So stuff can pass through that to do something. And now let's see. If we have J equals to 1, K equals to 0, we are actually, you know, remember J is S, K is R. So when J is 1, we are actually setting setting Q. We're actually setting Q, right? So we're setting Q. So Q is 1, Q bar is 0. And now let's see the feedback. So 0 will come back to here. 1 will feed back to here. And we know clock right now is 1, right? So it's 1, 0 here right now. And you are getting a 0 for the 3 input NAND gate individually. So you get a 0 for both of them. And then what's going to happen is you are getting a 1 and 1 here. So 1 and 1 will keep everything in memory. So which means whatever you have here, which is 1, 0, you know, the result were set previously, it's going to stay being set. So which means this status is pretty stable, which means it's going to work. If you have a J here to be set, have a 1 to set a circuit, you are going to set a circuit and it's going to be stable. Okay, no surprise. It's the same function as the previous SR latch, SR flip flop we learned, right? When you do that, it's going to be set and stable. So what if J is 0, K is 1? So we are trying to reset the circuit. And now let's see if that is stable. So keep in mind how I do the analysis. I'm just trying to analyze if it is stable. If it's stable, it's going to work. It's going to stay like that state in that state. So when we have K is 1, S is 0, J is 0, we are going to reset the result, and let's see if this is stable. So 0 will be fed back to here, you are getting a 0. 1 will be fed back to here, you are getting a 1. Okay, and 0 will kill the Nand gate, and 0 will kill the Nand gate, you are getting 1 ones. So it is pretty stable, it's a memory, it's going to memorize its status and will not change, being changed. So it's resetting Q and stable, it's pretty stable as that status. All right, now let's see, what about j equals to 0, k is to 0, what's going to happen? Definitely you have zeros for these two Nand gates, you are going to have ones here, so 1 will keep it memorize the previous state, right? It's a memory, no problems. Now the most tricky part, what's going to happen if you have this? What's going to happen? If you have a 1 1, right, you have to think about what the previous state will be. If the previous state here, if you previously, before you reach this state, j equals to 1, k equals to 1, if you have the circuit set previously, so you are going to have a 1 0 here, right? 1 0 here, and you have 1 1 right now, right? 1 1 right now, and you have 1 0 here. So 0 will be fed back to here, 1 will be fed back to here. What's going to happen? So 1 go back, come back here, 0 come back here. So 1 come back here, 0 come back here. And previously, what are these? What are they? So previously they are. No, not previously. You don't care about previously. You previously the output is 1 0. They're already being fed back. You got 1 0 here. But however, you have 1 1 for these two guys. So you have 1 0, 1 and 0 and 1, 1 and 1 and 1. So you are going to get a 0 here, and you are going to get a 1 here. So 1 0. Keep in mind, here's R, right? So you are resetting the circuit, which means if you have this after a few delay, it's going to feed back and change the result. You are going to reset it. Okay. So after reset it, what's going to happen? So 0 will come back to here. Will come back to here, becomes 0 right now, and 1 will go back to here, becomes 1. Right? So now you have 1 1, so you got a 0, 1 0, you got 1. And you are, if you have this status, it is trying to set the circuit. So now you can see it's gonna do this so on and so forth, which means Q will be toggled all the time after that. So now you get rid of the invalid status for that, but however, you are getting a toggled or oscillating output over there, so which can be used as a oscillator or something in the future. So now this is the JK flip-flop, and what are these applications and analysis you can do with it. So the bottom line is you know how that works, and you can do analysis on that, and also plus some kind of simulations with it, because we will need this kind of thing to build. Since we are learning from baby steps, we learn from the transistors and we build logic gates. So now we can use the logic gates to build some more complicated circuits, and we are going to use the flip-flops to build shift registers and counters in the future. So now let's do it really quick in LT-Spice to build yeah, we are going to do SR flip-flop really quick, okay, not the JK version. So SR flip-flop in LT-Spice. I just copy and paste the previous gates we built in here, and don't forget to include the model file in there. And now what I will do is I will start LT-Spice. Sorry, LT-Spice. I'll start a new schematic, and oh my goodness, so I don't have a Nand Gate here. So let's make a Nand Gate first, right? It's pretty simple though. Is that right? Nand Gate. I'm pretty curious about what's the circuit. Yeah, so there's no Nand Gate. It's just AND gate, but which is super simple. Let's do it. So the Nand Gate is nothing but just delete the inverter, then you are getting a Nand Gate. Okay, and I'm gonna move this VL to here. So that's a current VL. I'm gonna save it, and I will create a. Yeah, you don't have to create it. Let's just reuse the AND gate. Let's just copy and paste, and then I'm gonna rename it as Nand. Just make it match to that internal circuit, and I will come back here and try to add a bubble over there. So let's do that. So I need a circle, press C, draw a circle here, and I will move it to here, and I will save it. All right, so now we have the Nand Gate, and I shouldn't close out this file. So start a new schematic, and I will save it as, so make sure you save it to the same directory, and I'll name it as, we're trying to build up a SR latch, right? And we will do a simulation in there. And now, SR latch, we need four Nand gates. Go back here, Nand gates, 1, 2, 3, 4. All right, so that's 4 Nand gates, and definitely we need a power supply. Go back to the regular library. Find out voltage. You need this one, and also you need 2 signals for the S and R and 1 clock as well. So now let's name it as VDD, which for the power. I should move it. Sorry for that. I'm going to do it later. VDD for that. 1 VDD. Yeah, we can. You know what? We can put it here for now, and we can change the name later. VDD, and we will move this thing. Goodness. Move it up. Move it up. Move it here. All right. Makes sense. And then we need to ground everybody here. Ground it. Oh, no, I'll fix it later. Don't worry. Move it. Move it. All right, now feedback. Feedback. Here. And I want to move this guy a little bit up. And then connect that one to here. This one to here. And this one. Wait. No. F3. And that's S, that's R. Right, so now let's name it S. This is R. And we want to name this one as, oh no, not A, but S. And R. And CLK. Yeah, actually I prefer smaller case CLK. CLK. And I will copy this CLK and connect it to here. So you have a clock signal. And now we have the circuit already built up here. So before we move forward, we need to go to .op and give a model file. Oh, before we do that, let's right click to fix it. Control, yeah, I'll delete it. Dot include, Control Enter. So you're not closing the window, but just shifting the line. And then you do a dot transient analysis from 0 to 20, no, let's do 100 microsecond, and every 0.1 microsecond you want to plot a point. So that's a simulation code, and we need VDD to be 5 volts, and right click, we need V2 to be a signal. Go to advanced, go to pulse, and starting from 0, and V on to be 5 volts. So let's imagine what kind of simulation you want to do. So before you can set up in LTSpice, you need to plot it first, right? If you don't know what you are going to do, the software won't help you. Software is just a tool. Do whatever you ask the software to do. So for example, we want to just try to verify SR flip-flop. We have a clock, we have S, we have R, we have Q, and Q bar, right? These are the inputs, output. What kind of simulation you would like? So we want to verify if when clock is 1, right? So we have a clock. So when clock is 1, the circuit, the output will be set. Whatever it is right here, it's going to be set here. And then for when clock is 0, and if you are lucky, you have your S and R to be 0 as well, you are going to keep it. Yeah, you don't have to have this one to be 0. If you have this one to be 0, it's going to memorize at whatever previously. Okay. So we just want something like that, and we'll just create a waveform and see what's going to happen over there. So the question here is, do you want S and R to be slower or faster than the clock signal? So here's a question: you want this one to be really quick, really fast, or you want that one to be, yeah, let's just make the same frequency. I think that's fine. Just shift that a little bit. Shouldn't be a problem. Right. So now let's come back to the simulation. And we want to, let's just do 1 micron delay, no delay. And T rise 1 nano, just make it short. Can be 1 nano, can be several nano, doesn't matter. T on, let's make it 1 micron. And periods to be 2.1 micron. How about that? And I'm going to use the same signal for R. Right, I'm going to copy. Go to pulse, and don't do anything here, and then come out here and then copy and paste. So the only thing you want to do is change the delay a little bit. You can change it, you can shift it by 0.5 micron. So yeah, just make a shift. And for the clock, you exactly need, I think you need the same stuff. Yeah, but shift it by, do you want to shift this? Yeah, let's shift it 75 micron. Okay. And we are going to assign the name of the output to be Q, and here to be Q naught. Since you couldn't create a bar here, so just underscore naught. And let's run it and see. Unknown for you. What does that mean? Okay, it's here. That. Run it. Okay, now let's see. We have clock, we have S, we have R. I think we simulated too much here. Let's don't do one. Don't do that. Let's just do 20. Okay, let's rerun it. So last signal here, and Q bar. And so we have 5 signals. We need 5 plot pins. 3, 4, 5. Oh, now add traces. Add pin. So clock to put on the top, and S, and R, and Q, and Q not. So you can see this is you see a lot of spikes, but however you can see they didn't scale this y-axis really well. They are actually totally 5 volts. You know, it's 4.77 something. You know, stabilized at 5. If you change that one from 0 to 6, for example, so you can see that it's actually just 5 volts DC. Okay, and now let's see if that is valid. Looks like something is going wrong here because Q bar is not being inverted, which is pretty interesting. We'll see. So now we are going to change, right click and change the scale to make it visible on the top. So let's see, when clock is 0 here, and we expect the result to be a memory. So whatever has been there for S and R is going to memorize. Yeah, you know what's the problem? Because you start with a memory because you don't have any initial state in there in Q and Q bar. So that's why there you see a lot of errors over there. It's just not making sense. So we probably want your clock to be 1 in the beginning, and you don't want your pulses to be both zeros, right? So what you want to do is you can have 5 in the beginning and 0, right? So you are having a 1 1 somehow. You just make 1 to be 1 in the beginning, and you don't want your clock to be 0 in the beginning, so you want a 5 and 0, right? Start with a 5 and jump, and then drop to 0. Now let's run it again and see. So let's take a look at that if they're inverted. So are they? Yeah, they're inverted right now, so that makes sense right now. All right, so add plot pins. It's good to have this mistake so you know how to fix it on your own. This is online course, is gonna be tough if you don't know what's gonna happen, right? It's good to explore all these errors so you can fix it by yourself. S, R, Q and Q bar are getting inverted, which is correct because you have a 1 clock 1 here, you know, you enable that Nand Gate so you can and also you are not so you enable the Nand Gate, so that's why you can have something to be memorized, right? So even though you are having a 1 1 0 0 here, so 0 0 will have a 1 1 which will be a memory. I mean, they just automatically set up an initial state for Q and Q bar to be 1 0. Okay, but now it's start making sense. Let's do it from step by step. So for example, you already have an initial state for Q and Q bar, which is 1 0, right? So which means the result is being set. Okay, and now let's see. When clock is still 1, right? So 1 is being, which means it's being enabled, and now your S and R becomes 0 and 1, which means it's trying to reset the result. And now let's see if the Q is being reset. It is. Okay, so when after Q is being reset and clock becomes 0, you know, this is a super strong 0 here, which will kill all the Nand Gate and force that slash or the flip-flop to memorize the previous state. So which the previous state is 0 here, right? So it's going to be memorized. all along the way until here, because the clock is 0, it's trying to memorize that. And then at this time point, clock becomes 1, so your flip-flop come back to work again. And now let's take a look at what's the status here. It's 1, 0, so which means it's trying to set the result. So the result getting set, right? Which is making sense. And then you finally have 0, 0 afterwards. So which means it is going to memorize the 1 here. It's going to be memorized until here, and it is, okay? And here you have a status change because clock is still 1, so it's invalid, but you have your S and R signal to be swapped. So now it's trying to reset the signal, and you are getting a 0 here, okay? You can do it so on and so forth. It's going to work for all these signals. This is really the way I can think about that you can verify your flip-flop. It's kind of like in the sequence. So makes this a little bit difficult compared to the combinational logic. However, we are close to the end of semester for the online course. You just go forward to do this kind of simulation, but I'm gonna upload this simulation file beside the video here I'm recording, and the homework can be a little bit different from the SR flip-flop, but it will be really similar, and you will get a chance to build a better stuff, on your own, and try it out on your side. Okay. Thank you for watching. I'm gonna see you in the next video.